Hi everyone, Kevin here, back with video number 2 in module 8A on oxidation. Let's get going. You can stop and look at this for the topics we're covering in 8A. We are picking up with topic number 2 in this video about reduction potentials. Last lecture we talked about oxidation and reduction, and I showed you this image, and we said that as we go from methane, for example, to carbon dioxide, the carbon is oxidized. When we go the other direction, the carbon is reduced. We said that oxidation often looks like obtaining oxygen. You see oxygens on carbon dioxide, you don't see on methane. And conversely, reduction is often accompanied by hydrogen showing up, as we see when we go from carbon dioxide to methane. So why do molecules tend to get oxidized? And why do others get reduced? Molecules have a tendency to be reduced based on their chemical structure. It's inherent in who they are. The reduction potential measures their tendency to be reduced. It's a number we give it. In lecture, we're going to talk about how reduction potentials are a little like chocolate. Just an image that may help remember this. But for now, let's talk about reduction potentials. Let's take this example here, the oxidation and reduction to make table salt. So if you took sodium, solid sodium metal, and you reacted it with chlorine gas, that would be Cl2 in the form of the gas, so Cl2 gas. You react that with solid sodium metal, and you'd get an oxidation reduction reaction. The sodium would lose electrons, it would become oxidized, right? Oil rig, oxidation is loss. The chlorine picks up an electron and becomes reduced. Reduction is gain. So why does this happen? Why does sodium lose the electron while chlorine gains the electron? It has to do with the properties of sodium and chlorine, and it has to do with the energy levels of the electrons that surround those two atoms. So let's look at this periodic table down here. Element number 11 is sodium. Sodium has one electron in its valence shell, its outer shell. That's shown by this red sphere here, this red circle. That's the one electron in the outer shell. That's a pretty high energy electron. Now look over here at chlorine, element number 17. Its outer shell has 7 electrons, right? 7 of these red circles. So it's missing one. There's one spot in here that wants another electron, another red circle, right? And that will fill that outer shell. And we know that atoms are very, very happy campers when they have a filled outer shell. So when that electron adds to chlorine, the energy level of that electron is lower than when the electron is in sodium. Sodium has just one electron in its outer shell. If it gives up that electron, if it gets rid of it, I'm trying to draw an arrow out, then the remaining shell would be this tan shell, and that would be a filled shell. And sodium would be a happy camper too. So the nature of these elements means sodium is happy to give up its outer electron, and chlorine is very happy to pick it up. So sodium has a low potential to be reduced. Sodium has a low potential to pick up an electron. In fact, it wants to give up an electron. Chlorine has a high potential to be reduced because it really wants that electron. It wants that extra electron. So it has a high potential to be reduced. So we can do experiments and actually give numbers to the relative potentials to be reduced. Sodium with a very low potential to be reduced. Chlorine with a very high potential to be reduced. And it's just based on who they are, the nature of who they are. Here is a table of some of those numbers. So let's look at a couple things in the table. Here's the potential for chlorine to be reduced right here. 1.36, positive number. All right, and that's for chlorine to pick up 2 electrons. So Cl2 gas picks up 2 electrons. It becomes 2 chlorine ions. Sodium, on the other hand, is way at the other end of the scale. The potential for sodium to pick up an electron is minus 2.71. So very low electron potential in sodium, a very high electron potential in chlorine. Now these numbers are relative to one another. In this particular scale, we have picked the scale, we've picked as 0 on our scale the tendency for 2 protons to pick up 2 electrons and become hydrogen gas. Okay? We could pick other things as 0 on the scale, but the difference between the reduction potential of chlorine and the reduction potential of sodium would be the same no matter what we picked as 0. Okay, so that gap is huge. Chlorine's high, 1.36 positive, sodium is low, 2.71 negative. So chlorine wants to be reduced, sodium wants to be oxidized actually. It wants to give up its electron. It does not want to be reduced. So the way this equation is written here for sodium, it shows sodium picking up an electron. It doesn't really want to. It shows the sodium ion actually picking up electron to become the neutral atom. It doesn't really want to do that. It's really happy with that electron gone. Why? It has a complete outer shell. Rather than one electron in the outer shell, it's got a nice complete outer shell. So sodium plus is very happy being sodium plus. Chlorine minus is very happy being chlorine minus. That's it for video 2 in Module 8A. I'll see you in video number 3. Thanks for watching.